So we're going to have a little bit of a talk about how to find the empirical formula of a compound once we're given the percentage by mass of each of the elements in the compound. So to start off, we know that an empirical formula gives the simplest whole number ratio between elements in a compound. So empirical formula are always used for ionic compounds because we know that ionic compounds don't have sort of molecules or small groups of elements. They only have sort of big lattice structures, and so the only way to analyze the composition of an ionic compound is to look at the ratio between the ions in the compound. So for that reason, empirical formulae are always used for ionic compounds. For example, if we look at sodium chloride, there aren't, if we have a big chunk of solid sodium chloride, there aren't, billions of molecules where we've got a sodium bonded to a chloride, but rather we've just got a big block or a big sort of cube grid-like structure of sodiums and chlorides all bonded to one another in a 1-to-1 ratio, making this NaCl an empirical formula. Now, it's important to note that empirical formulae are in fact different from molecular formulae. Molecular formulae show the exact number of atoms of each element in a molecule of a compound, whereas the empirical formulae may in fact be different to the molecular formula. Okay, because the empirical formula just looks at the ratio of the makeup of a substance, whereas the molecular formula really gives you, the number of atoms scattered around within a given substance. Okay, so we're going to sort of go through this a little bit later, but first what we're going to look at in this video is how to find the empirical formulae of a substance using the percentage by mass of the elements inside it. Okay, so basically if we're given percentage by mass, so say we're told that a certain compound is a certain percentage made up of element A, it's got a certain percentage made up of element B, and a certain percentage of element C. Now these percentages are percentages by mass. So basically, say this is 13% element A, then that means 13% of the mass of this compound is caused by the mass of element A. And so what we want to do, we know that this ratio in empirical formulae is the ratio between actual sort of ions or the ratio between actual atoms or ions. So this ratio depends not on the mass, but on the number of moles or the number of actual particles. So for this reason, we need to convert this percentage by mass. So this is by mass. We need to convert this to a molar ratio. We want to work out sort of the ratio between the number of moles of each of A, B, and C in this compound. So we're going to go through an extended example on how we do all these calculations. So let's say, for example, that we are told that we get a compound, and we've been told that the compound has been analyzed, and it's been found to contain 3.1% hydrogen. It's been found to contain 31.6% phosphorus, and it's been found to contain 65.3% oxygen. So here we're starting with the percentage by mass. So 3.1% of the mass of this compound is hydrogen, 31.6% of the mass of this compound is phosphorus, and 65.3% of the mass of this compound is oxygen. So this is the percentage by mass. Now what we want to do, the easiest way to deal with this kind of stuff, percentages can be a little bit confusing, and we want to sort of convert this to an actual mass so that we can get on to the molar ratio. So the best way to do that is to consider a 100-gram sample. 100 gram, we choose 100 because obviously percentages revolve around that number and it makes everything pretty easy to work out. So if we look at a 100-gram sample, what we're going to do is we're going to work out the number of grams of each of these things, each of these elements, in a 100-gram sample of this compound. So obviously, if we have 100 grams of this compound, we know 3.1% of this compound is hydrogen, then in this 100 grams, we're going to have 3.1 grams of hydrogen. Similarly, we're going to have 31.6 grams of phosphorus and 65.3 grams of oxygen. So now what we want to do is we want to figure out the number of mole that we have of each of these three elements in the 100-gram sample. So we convert that to number of mole. So we know that N is equal to M over MM. So number of mole here is equal to 3.1 over 3.0, which is equal to 1.03 mole. Okay, we do the same thing with phosphorus. We say N equals 31.6 over 31.0. That's equal to 1.02. So we've got a bit of a mistake back here. This was quite a poor error there. So that should be, we know the molar mass of hydrogen is not 3.0 grams, it is 1.0 grams. So if we have 3.1 divided by 1, we get 3.1, obviously. Okay, the molar mass of phosphorus is actually 31.0, that's correct. So 31.6 divided by 31.0 tells us that we have 1.02 mole of phosphorus in this 100-gram sample. If we do the same for oxygen, we have 65.3 divided by 16.0, and that gives us 4.08 mole. So we can see here that if we go off these ratios, we've got, if we go 3 times 1.2, so what, well, ignore that. What we want to do is we want to then go to the molar ratio. Now you can see here, we know we've done all these calculations correctly, so we can be confident in these numbers of moles in the 100-gram sample here. And so, although it's not exactly perfect, we have pretty much very close to exactly, but not quite, a ratio of 3 to 1 to 4 of hydrogen to phosphorus to oxygen. Okay, so we've got 3.1, 1.02, and 4.08 mole. And so, 3 times 1.02 is 3.06, but that's, pretty much 3.1. If we were to say 4 over 3 times 3.1 is going to be approximately equal to 4.08. So it's all pretty much spot on. And so from that, we figure out that the ratio between the hydrogen, the phosphorus, and the oxygen is the ratio 3 to 1 to 4. And so we know that the empirical formula is basically just the simplest whole number ratio between elements in a compound, and we've seen empirical formula before. So we know that our empirical formula is H3PO4, or phosphoric acid. Now, once we get to this step, we may have set our page a little bit different. We may have had, the phosphorus column here, the hydrogen column here, and the oxygen column here. And so it might have come out as 1 to 3 to 4. And so if that's perfectly fine, we could perfectly easily write the empirical formula as PH3O4, or any other sort of permutation of these different elements. However, once we see this, we not only we were lucky enough to already have it in the right order that the formula of phosphoric acid is written in. However, this is similarly a good and correct empirical formula for phosphoric acid. However, based on these calculations, we know that this is a true empirical formula, but we know that phosphoric acid is usually written as, or always written as, H3PO4, so we can rewrite it like this. So basically, these are sort of the 5 steps that I've outlined on each line of working down the left-hand side here. So we're given a percentage by mass. We're given a percentage by mass. And the obvious thing to do there is convert that to an actual mass out of a 100 gram sample. So all we have to do is rewrite 3.1% as 3.1 grams. We're converting the percentage by mass. We're using that figure to work out the number of mass of each element that we would have if we had a 100 gram sample of the compound. Next, we use these masses to figure out the number of mole of each of these elements in the 100 gram sample. Now that we've got the number of mole in one sample, we can figure out the ratio between those numbers of moles, and from there, the empirical formula. So these are basically the steps that we follow to find the empirical formula from the percentage composition by mass. Okay, and this molar ratio step, this is basically in any question where we want to find the empirical formula of a compound, this molar ratio step is sort of the step that we strive for. This is what we're sort of looking for throughout our calculations. It just so happens that when we're given the percentage by mass, this is the means by which we get to the molar ratio. But in any other question, where we're asked to find the empirical formula of a substance by other means, besides the percentage composition by mass, this molar ratio is what we ultimately want to find, because from that molar ratio, we can find the empirical formula. So we're going to go through, other situations, other contexts where we'll have to find the molar ratio. But in this case, if we're finding the empirical formula from the percentage composition by mass, we use this set of steps to get there, and so we ultimately have, in this example, phosphoric acid. We've obtained that from this percentage by mass breakdown up here.